Electric cars represent a transformative shift in the way we think about personal transportation and energy use. At their core, electric vehicles, EVs, are designed to operate with much greater efficiency than their internal combustion engine, ICE counterparts. This efficiency stems from the fundamental differences in how they convert stored energy into motion. While conventional vehicles burn fossil fuels to generate mechanical energy, a process fraught with energy losses, electric cars rely on batteries and electric motors that can utilize energy far more effectively. One of the most significant ways electric cars save energy is through their highly efficient powertrains. In a typical gasoline-powered vehicle, only about 20% of the energy stored in the fuel is actually used to move the car. The rest is lost as heat, noise, and friction within the engine and exhaust system. In contrast, electric motors convert over 85% of the electrical energy from the battery into movement. This dramatic improvement in efficiency means that for the same amount of energy input, an electric car can travel much further than a vehicle powered by an internal combustion engine. The reduced energy loss not only conserves resources, but also translates into lower operating costs for drivers. Another crucial aspect of the energy-saving potential of electric cars lies in regenerative braking. Unlike traditional vehicles, which dissipate kinetic energy as heat during braking, electric vehicles employ systems that capture this otherwise wasted energy. When an EV slows down, its electric motor runs in reverse, acting as a generator to convert kinetic energy back into electricity, which is then stored in the battery for future use. This process can recapture a significant portion of the energy used to accelerate the car, especially in stop-and-go urban driving conditions. Over time, regenerative braking contributes to substantial energy savings and extends the range of electric vehicles. The architecture of electric vehicles also plays a role in their superior energy efficiency. Electric cars are often designed with aerodynamics and weight reduction in mind, using lightweight materials such as aluminum and composites. These design choices reduce the amount of energy required to overcome air resistance and inertia, allowing the vehicle to travel further on a single charge. Additionally, the compact nature of electric drivetrains frees up space and allows for more flexible vehicle layouts, which can further improve efficiency by optimizing weight distribution and reducing drag. Beyond the individual vehicle, the energy-saving benefits of electric cars extend to the broader energy ecosystem. Electric vehicles can be charged using renewable energy sources such as solar, wind, or hydroelectric power. As the grid becomes increasingly green, the total energy footprint of electric cars continues to shrink. Unlike internal combustion engines, which are locked into using petroleum-based fuels, EVs can take advantage of advances in clean energy generation. This flexibility means that the environmental and energy-saving benefits of electric cars will only grow as society transitions to more sustainable sources of power. Moreover, electric vehicles have fewer moving parts than traditional cars, which leads to less energy lost to friction and mechanical inefficiency. Internal combustion engines require complex transmissions, exhaust systems, and cooling mechanisms, all of which consume energy and add weight. Electric cars, by contrast, often use simpler single-speed transmissions and require less extensive cooling systems, further reducing parasitic energy losses. The simplicity of the electric drivetrain not only enhances efficiency, but also reduces maintenance needs, which indirectly saves the energy and resources associated with manufacturing and replacing parts. The way electric cars interact with the grid also opens new avenues for energy optimization. With the advent of smart charging and vehicle-to-grid (V2G) technologies, electric cars can help balance energy demand and supply. For instance, they can charge during periods of low electricity demand or when renewable generation is high, and even feed energy back into the grid during peak times. This bidirectional flow of energy helps smooth out fluctuations in electricity production and consumption, reducing the need for inefficient peaker plants and minimizing overall energy waste. Electric cars also encourage more thoughtful and efficient use of energy at the societal level. Because charging infrastructure and battery range are still developing, EV owners often become more aware of their driving habits and energy consumption. This consciousness can lead to changes in behavior, such as combining trips, using public transportation for longer journeys, or adopting other energy-saving practices. As a result, the transition to electric vehicles can foster a culture of conservation and efficiency that extends beyond the vehicles themselves. The environmental impact of electric cars is closely tied to their energy-saving attributes. By consuming less energy per mile and enabling the use of cleaner energy sources, EVs contribute to lower greenhouse gas emissions and reduced air pollution. This is particularly important in urban areas, where traffic emissions are a major source of smog and health problems. Cleaner air and a smaller carbon footprint are direct results of the improved energy efficiency of electric vehicles. It is also important to consider the life cycle of electric cars when evaluating their energy savings. While battery production does require significant energy and resources, studies have shown that the total energy use over the lifespan of an electric vehicle is still far lower than that of a comparable gasoline-powered car. As battery technology improves and recycling processes become more efficient, the energy costs associated with manufacturing and disposing of EVs will continue to decline, further enhancing their net energy savings. In addition, the modular nature of electric vehicle batteries opens the door to second life applications. After their useful life in cars, batteries can be repurposed for stationary energy storage, supporting renewable energy integration and grid stability. This extended utility maximizes the energy investment made in producing the batteries and reduces the need for additional resources, amplifying the overall efficiency gains associated with electric vehicles. The adoption of electric vehicles also has the potential to reshape urban planning and infrastructure in ways that promote energy efficiency. As cities invest in charging stations, prioritize electric public transit, and create incentives for EV ownership, they can reduce traffic congestion and encourage the use of shared mobility solutions. These changes can lead to more compact, walkable communities where energy use for transportation is minimized. The synergy between electric vehicles and smart urban design can create a virtuous cycle of energy savings and sustainability. Furthermore, the ongoing development of advanced battery technologies promises to make electric cars even more energy efficient in the future. Innovations such as solid-state batteries, improved energy densities, and faster charging capabilities will allow EVs to travel further on less energy and reduce losses during charging and discharging. These technological advancements will not only enhance the appeal of electric vehicles, but also deepen their contribution to energy conservation. Government policies and incentives play a crucial role in accelerating the adoption of electric vehicles and realizing their energy-saving potential. Subsidies for EV purchases, investments in charging infrastructure, and regulations that encourage the phase-out of internal combustion engines all help to create an environment where energy-efficient transportation can flourish. As more countries and cities commit to electrifying their vehicle fleets, the cumulative energy savings will become increasingly significant on a global scale. It is also worth noting that electric cars can catalyze innovation in other sectors. For example, the push for better batteries and more efficient power electronics has spillover effects in renewable energy, consumer electronics, and industrial applications. The lessons learned from optimizing energy use in electric vehicles can inform broader efforts to improve efficiency and sustainability across the economy. Despite their many advantages, it is important to acknowledge the challenges that remain for electric cars. Battery production, raw material extraction, and the current limitations of charging infrastructure all present obstacles to maximizing energy savings. However, ongoing research, investment, and policy support are steadily addressing these issues. As the technology matures and scales up, the energy-saving benefits of electric vehicles will become even more pronounced. In summary, electric cars save energy through a combination of highly efficient powertrains, regenerative braking, lightweight and aerodynamic designs, and the ability to integrate with renewable energy sources. Their simplicity, lower maintenance needs, and potential for smart grid interaction further enhance their efficiency. As battery technology advances and supportive policies are implemented, the energy-saving impact of electric vehicles will continue to grow. Beyond the technical aspects, the shift to electric cars encourages a broader cultural embrace of energy conservation and environmental responsibility. Together, these factors position electric vehicles as a cornerstone of a more sustainable and energy-efficient future for transportation.